Hello friends, we have already discussed about dynamic recrystallization, the microstructural part. Okay, in today's lecture now I want to discuss about the stress and strain behavior as well as how I can find out the critical strain or stress required for dynamic recrystallization. Now we have already seen these micrographs, these stress strain curve or flow stress curves. Okay. And you can see when you have discontinuous dynamic recrystallization, the stress strain curve or the flow stress curve has this kind of a peak, okay, and then it comes down and more or less it becomes a steady state. Okay. And as a function of temperature, if you see the temperature is increasing, so flow stress is reducing. Okay. So, you can also see that this now hump or this peak is of kind of lower magnitude. Okay. And as you increase the temperature more, now you see something very interesting, that now there are oscillation in the flow stress curves. Okay. There are oscillation in the flow stress curves. Okay. So, a characteristic feature, if you want to define, it is basically a broad peak, okay, and then the steady state flow, and deformation at lower z as Zener-Holloman parameter, we already know this. You will be seeing the multiple peaks. Okay. So, the lower z means strain rate, either strain rate low or temperature high. So, the temperature effect you can see here, as temperature is increasing, you have started seeing these multiple peaks. Okay. Similar behavior you may be able to see when you are reducing the strain rate. Okay. So, with lower z, okay, always remember lower z means strain rate is low, temperature is high, you will start seeing instead of one single broad peak, you will start seeing multiple peaks. You can also understand that for dynamic discontinuous dynamic recrystallization to initiate, okay, we will require some critical strain. Okay. Now, I can just define a critical strain just before the peak stress. So, peak stress is where my this slope of this particular curve is 0. So, let us say this is my peak stress. Okay. Then the critical strain to initiate the dynamic recrystallization, you can understand that dynamic recrystallization is more or less complete here, that is why the flow stress has started decreasing after that. Okay. So, the dynamic recrystallization must have started initiated somewhere at this point, okay, but we are not sure which this strain is right now. Okay. We will find out how I can find out that. Okay. Let us say that is some critical strain. Okay. So, one of the objective of this particular lecture is to also find out this critical strain or critical stress. Okay. So, corresponding stress will be your critical stress to initiate the dynamic recrystallization. So, that we must know as an engineer that what kind of strain I have to impose in the material to start the dynamic recrystallization process. Okay. So, recrystallization kinetics, if you see, kinetics means how fast the recrystallization after start, how fast it can complete. Okay. And usually it also follow the S-shaped curve as in phase transformation. Okay. So, if I kind of have the complete recrystallization here, 0 recrystallization here as a function of time, it will have some behavior like this, a S-shaped curve. Okay. So, the kinetics, that means the time required to from start to finish, okay, will be will decrease with initial grain size. Okay. So, at higher deformation temperature, it will take lower time to complete the recrystallization process. Now, the nature of flow stress curve, as we have just seen, okay, at low stresses, as you have just seen, okay, that so stress and strain, okay, and you had this kind of multiple peaks. Okay. This will happen at lower stresses or lower z values. So, the first how this multiple oscillation takes place, that is what we want to explain. Okay. So, as you can understand that the flow stress increases as the dislocation density increases in the material. Okay. So, dislocation density is increasing and the flow stress is increasing because of that, and when the recrystallization has happened, now the grain size has refined and grains are relatively strain free. Okay. That means the flow stress will come down. Okay. Then the next cycle of the recrystallization will takes place. Okay. And you will have again a peak. Okay. Again the recrystallization is complete, it will come down, again the next cycle of recrystallization will takes place. Okay. So, this repeated change in dislocation density, okay, increase, and after recrystallization it will decrease, okay, give rise to these oscillations. Whereas, if you see the single one broad peak when you see, okay. So, in this case what happens is that after the first recrystallization cycle, okay, before it completes, okay, the next recrystallization cycle starts in the already recrystallized grains. Okay. So, you should understand that recrystallization from start to finish, it has some finite amount of time or duration is there. Okay. So, if after let us say 60% of material has already recrystallized, 30-40% is still remaining, it is getting recrystallized. Suppose in this recrystallized, the 60% recrystallized grains, again the next cycle of recrystallization happens. Okay. So, then there is a continuous, or the material will always be in the partially recrystallized condition. Okay. And because of that, you will see after the first recrystallization and the drop in the stress, you see more or less a steady state condition. Okay. Because of the at some part of the material, there is always some recrystallization cycle is going on. In some part it is coming to end, in some part it is just starting, already recrystallized grain are again starting to build up the dislocation density and getting into recrystallization mode. At some other end already the recrystallization is about to complete and so on. So, it is a continuous recrystallization or dynamic balance between recrystallized and unrecrystallized volume give rise to a steady state. Whereas, in oscillation, after completion of one cycle, the whole material gets recrystallized more or less, then the next cycle again the dislocation density increases, okay, and then again the recrystallization happen. Okay. So, at lower stresses this will happen, that means at lower strain rate and higher temperatures, okay, where you have sufficient amount of time to build up the dislocations. Okay. At higher stresses, that means higher strain rate and lower temperatures, you will have this one single broad peak, okay, and there will be continuously some recrystallization must be happening at some part of the material. The other parameter is initial grain size. Larger initial grain size promotes single peak flow curve, and smaller initial grain size promotes multiple peak. Okay. So, there are two effects for stress and initial grain size. So, if you combine both, okay, in fact you can divide them into two regime here. Okay. So, on y axis you can see the z parameter, or you can also say in terms of flow stress, as already we have discussed many times that my stress is a function of z, and on the x axis you have initial grain size. Okay. So, if initial grain size is more, flow stress is low, okay, you will have single peak. Okay. If the initial grain size is small, okay, and my stresses are low or high, okay, you will have multiple peaks. Okay. So, you can divide these two deformation behavior into two regimes using the idea of flow stress and grain size. Okay. And this is your demarcation line. Okay. Above this you will have single peak curve, below this you will have multiple peak curve. Now, how to determine the critical strain for recrystallization in single peak flow stress curves. Okay. So, this is what we want to know, that at what point, okay, which is that critical strain where the recrystallization has started. Okay. And because you have to corroborate all these ideas with microstructure. Actually, we usually say that at least like 4 or 5% of material has recrystallized. So, that I can in a microstructure I should be able to identify that yeah, some few grains have recrystallized. Okay. If the nuclei is very small, if you are not able to see through normal optical microscope or SEM, okay, then it does not make any sense. Okay. So, usually it is like around 5% or so recrystallization. When it has happened, then we say that it has initiated. Okay. But we want to know this from the flow stress curves also. So, basically we want to know that what is the critical strain, okay, because right now I do not have any clear way of telling that or whatever way I am telling is a ambiguous way that from the slope change I am trying to figure out that okay, at this point somewhere the critical strain is reached and the recrystallization will take place. So, in general recrystallization starts when slope of the flow curve changes. Due to recrystallization, strain hardening should decrease. Okay. So, when recrystallization happen, you have strain free grains, that means the strain hardening should decrease. So, critical condition for initiation of DRX can be identified from the inflection point on the strain hardening rate. So, if I see a sharp change in the my strain hardening rate, okay, and how I am defining the strain hardening rate? I am defining by the slope of this particular curve. Okay. So, at any point I can take the slope. Okay. What is that slope? So, if I take slope here, you can see that strain hardening is more. If I take slope at this point, you can see the slope is coming down, that means the strain hardening rate is coming down, okay, and that is given by theta here. So, theta is equal to del sigma by del epsilon versus flow stress. So, if I plot something like this, okay, between the flow stress and this strain hardening rate, I should be able to see from the inflection point that where there is a change in the hardening rate, okay, because there the recrystallization must have started, okay, and from there we should be able to tell, okay, this is my critical strain or critical stress to initiate the recrystallization process in the material. Okay. So, I will take I will explain it on the monitor itself now. Okay. So, basically you have this single peak curve, okay. This is my epsilon, this is my sigma. Okay. So, this is my sigma p, okay. And how I can find out the sigma p? Very simple, where the strain hardening or there is no hardening or the slope is 0. Okay. So, sigma p should be associated with where the d sigma by d epsilon is 0. Okay. The stress associated with that will be equal to sigma p. Okay. So, somewhere here is my sigma p and somewhere here is my epsilon c, and stress associated with this is sigma c. Okay. So, first I will plot, okay, the flow curve in another form now. I will take the differentiation d sigma by d epsilon, which is theta. Okay. So, I want to now plot theta versus sigma. Okay. And if I plot that, it will I am just giving you a rough estimate of that. Okay. The flow curve should be something like this. Okay. And you can see that there is some inflection point at somewhere here, where the slope is changing from one type of slope to another type of slope. Okay. So, at that somewhere, okay, my slope should be 0 because it is changing the direction from one side to another side. Okay. It is going like this and then it is changing the direction. Okay. Another interesting thing is that if I want to plot the same curve for a DRV curve, okay, it will be a simple curve like this. Okay. There will not be any inflection point, okay, because if you remember for dynamic recovery, we showed curves like this, okay. Some strain hardening and then the steady state condition, okay. So, on this type of curve theta versus sigma, it will be just one straight line, whereas in recrystallization, okay, you will see a inflection point like this, okay. Now, actually if you see the data which you are getting from the machine and that you are plotting, that data will be very some kind of this kind of variation will be there, okay, large variation will be there, okay. You can find out the slope and just plot it, okay. So, basically you fit a smooth curve on this kind of very varied data, okay, and to plot us this kind of slope, usually we take some polynomial equation, okay. So, for example, in this case for plotting this particular curve, we have taken a polynomial equation of third order, okay. So, cubic equation basically, okay. So, it will have some relationship like this, okay, sigma cube and the A, B, C, D are constants of material, okay. And now to find out this inflection point, that where actually it has started, okay, where the slope is changing, let us again differentiate this also with sigma, okay, this particular equation. So, it will be now 3a sigma square 2b sigma plus c, and d is a constant. So, it will become 0, and I can again differentiate it to get sigma a plus 2b, and again c is a constant. So, it becomes 0, okay. So, if I plot this the curves, okay, for example, this d theta by d sigma, okay, it will be come something like this, okay. So, it has some minima here, okay, and this minima will have the slope of this will be 0 obviously, okay. So, this is also plotted as a function of sigma. So, where it is the slope of this particular curve between d theta by d sigma and sigma, okay, where it is giving you 0, that is the point where it has changed the slope, okay, and that is my inflection point, okay. So, this is actually should be, now I can say, and now see I am putting it as sigma c to be equal to 0, okay. So, I am putting this particular as 0, okay, and sigma I am changing to sigma c now. So, sigma c becomes b minus b upon 3a, okay. So, from these constant I will be able to find out that what is the critical strain for initiation of recrystallization, and correspondingly I can find out what will be the critical strain for initiation of recrystallization, okay. Another interesting thing is, if I plot sigma c as a function of z, okay, you will get a straight line. That means, at different Zener-Holomon parameter, or if I increase the Zener-Holomon parameter, my stress to initiate the or critical stress to initiate the recrystallization also goes up, okay. As you can understand, as I am increasing the z, that means I am increasing the strain rate and I am reducing the temperature. So, obviously, my stress to initiate or critical stress to initiate recrystallization will keep going up, okay. Now, same thing we can do for strain also. Some interesting type of curves are there for strain, okay. So, if I plot the same d theta by d sigma, but now as a function of strain, okay, I will see some curve like this, okay, where this is very close to 0, okay. And this is some strain star, and this is the steady state strain, Okay. And this also gives me about the kinetics of the deformation. If I plot, okay, so where it is reaching the steady state of strain, okay, at that point I will be completing my recrystallization process. So, this is 1, this is 0, okay, and this will be friction recrystallized, okay, and this is my time, okay, and somewhere here it will be able to complete 50% of strain, okay. So, it will start something like this and complete something like this, okay. So, this is a typical S shaped curve for the kinetics. So, I will be also able to find out that what is the kinetics of the recrystallization process, okay. So, this is what I have already discussed with you, okay. So, with this we are able to see that what is the critical strain and critical stress for recrystallization process, okay. By doing some simple mathematics here, I am able to find out that what parameters will be able to give me the critical stress, and correspondingly there will be a critical strain, okay. And if I want to find out the kinetics of the process, okay, then I have to plot against the same d theta by d sigma as a function of strain rate, strain, okay, and that will give me that what will be the kinetics of the deformation process. And as you can understand that as I am going to increase the temperature, okay, the kinetics will be faster, okay. So, it will go towards the lower time scale, okay. So, this kind of analysis will be able to give us that what will be the critical conditions of deformation to get a recrystallized microstructure, and what amount of strain I have to impose in the material, okay, to get this kind of recrystallization. And always as a design, if you are designing the process, okay, you always have to keep an eye on the flow stress part, okay. So, suppose we know that at lower temperature it will be the kinetics will be faster, okay, but we also know that the stresses will be higher. So, when you are designing a process, okay, so if stresses are higher, your rolling mill, all the parts which are used in the deformation process have to be designed for that kind of stress, okay. So, there is always a kind of a balancing act here to find out the proper condition of deformation to get a recrystallized microstructure in the material, okay. So, thank you. With this I am ending this lecture.